So in this part of the lesson, I'm going to summarize some of the ideas about factoring. I'm going to talk about some introductory examples, and then I'm going to discuss a strategy you can use when approaching a factoring problem, and finally work a couple more examples using this strategy. So in the first couple problems here, we're going to have a factorization that is incorrect in some way. And what we're going to be doing is discussing what went wrong in each of the following factorizations. Once we've discussed that, we want to try to redo each problem correctly. So the first problem we're going to look at is the trinomial x squared plus x plus 7, which has been factored as x times the binomial x plus 1 plus 7. Well, what went wrong here? Well, what's on the right side of that equation is not a factorization. If we look at this, we have an addition sign outside the grouping symbols. The primary operation is addition, not multiplication, which we would expect in a true factorization. So the expression on the right isn't factored. We have x times x plus 1, which is a factorization of just the first two terms, but the whole expression is not factored. So how could we do this problem correctly? Well, let's look back at the trinomial, x squared plus x plus 7. In order to factor that, we would need to find integer factors of 7 that add to 1. Well, the only integer factors of 7 are 1 and 7, which add to 8. So in this situation, we have a trinomial that does not factor. So the trinomial x squared plus x plus 7 is prime. Now when Steve, Candace, or I are teaching Math 65 in a classroom, we often see this on our students' exams. And I think what happens is that a student encounters a prime trinomial and panics a little bit and just wants to do something to make the answer look factored. We have some checks to determine whether or not a trinomial is prime. So if you're just systematic about it, you can figure out whether or not the trinomial is prime or if it can factor. Here's another example. We have a trinomial on the left and a factorization, a true factorization on the right. If I do a check to see if the factorization is correct, x plus 7 times 3x minus 6, product of the first terms, 3x squared, add the product of the outside term, add the product of the inside term, and add the products of the last terms. And that is indeed what I have on the left-hand side. So what's wrong with this? Well, what's wrong is that factor of 3x minus 6. Both terms in that second binomial factor share a common factor of 3, which could be factored out. So this expression is factored, but it's not completely factored. In order to completely factor this expression, I need to pull out that factor of 3 from the second binomial factor. So the correct result here would be x plus 7, and then factoring out that 3. And I probably would rewrite this with that constant factor out front, just because that's the way I'm accustomed to seeing it. And this is the correct factorization of that trinomial. In the next couple of problems, we're going to talk about perfect square trinomials. The following trinomials are going to have a missing term or perhaps a missing coefficient of a term. And we want to determine the term or terms that we would need in order to create a perfect square trinomial. Let's look at an example. X squared plus 10x plus blank. What needs to go into the blank to make that a perfect square trinomial? Well, remember the form. The form is a squared plus 2ab plus b squared. We're looking for the b squared term. Well, clearly a is x in this case, and the coefficient on the linear term is 10, which is going to be twice b. So b needs to be 5. So what I'm going to add to x squared plus 10x to make it a perfect square trinomial is 25. And if I factor this, I get that perfect square. x plus 5 quantity squared. Let's try another one of these examples. X squared minus 18x plus blank. Very similar, except now we have a perfect square trinomial in the form a squared minus 2ab plus b squared. We're looking for that b squared. Well, what's b? Well, that coefficient, negative 18, is going to be twice b. So in this case, b will be 9. So to make this a perfect square trinomial, I'm going to add 9 squared, which is 81. And this will factor into x minus 9 quantity squared. If you multiply out x minus 9 times x minus 9, you'll get back the x squared minus 18x plus 81. One more example, similar. Here we have a trinomial that we want to get a trinomial in the form a squared minus 2ab plus b squared. Now we need to fill in b squared. A in this case is 2x. We know the coefficient on the linear term. So we know that negative 2ab, that has to equal the opposite of 12x. We don't know b, but we do know that a is 2x. So the opposite of 2 times 2x times b has to equal negative 12x. Well, look at that equation. What does b need to be in order to make the two sides of this equation equal? Well, b is going to have to equal 3. So b squared will be 9. And if I factor this, this will factor into a minus b quantity squared. A is 2x in this problem, and b is 3. If you expand that, you'll see we get back our perfect square trinomial. So I call these last couple of problems factoring squared, because some students look at them and think these are really hard questions. But if you're very systematic about factoring trinomials, these are very easy questions. What we're being asked to do is to determine the values of k that make the following trinomials factorable. Let's look at an example. X squared plus kx minus 20. We want to know what are the values of k that will make this trinomial factorable. Well, let's think about how we would go about factoring this if k was some number. What we would do is we would look at the product of 1 and negative 20 and look for integer factors that add to k. Well, let's look at all the integer factors of negative 20. Negative 20 and positive 1. Negative 10 and positive 2. Negative 5 and positive 4. Negative 4 and positive 5. Negative 2 and positive 10. And finally, negative 1 and positive 20. Let's see what those add up to. Negative 19, negative 8, negative 1, positive 1, positive 8, positive 19. So it seems that there are 6 possible values of k that will make this trinomial factorable. So the possible values for k are, let's see, we have both positive and negative 1. We have positive and negative 8. And finally, we have positive and negative 19. What this means is if I see the trinomial x squared minus 19x minus 20, for example, that's factorable. But based on the work we've done, if I see the trinomial x squared minus 15x minus 20, or even let's say plus 15x, that trinomial is going to be prime because 15 is not in our list of values for k. Let's do one more of these. Again, if we're very systematic, this is an easy question. We want to find the values of k that will make this particular trinomial factorable. So if I multiply 5 times 8, that's 40, and I'm looking for integer factors of 40 that add to k. Now 40, the integer factors could either be both positive or both negative. I'm going to start with the positive factors of 40. So 40 and 1, 20 and 2, 3 doesn't divide into 40 evenly, 10 and 4, 5 and 8, or 8 and 5, 6 doesn't divide into 40 evenly, 7 doesn't divide into 40 evenly, and when I get to 8, I'm back to 8 and 5 in my list. When I add these, I get 41, 22, 14, and 13. Now let's think about the negative integer factors of 40. Well, negative 40, negative 1 multiplied to 40. They add to negative 41. So my values of k will not just be 13, 14, 22, and 41, but also negative 13, negative 14, negative 22, and negative 41. So there are many values of k that will work. And I'm just going to list them. Both positive and negative 13, positive and negative 14, positive and negative 22, and finally positive and negative 41. So we have 8 trinomials of this form that will be factorable. So I'm going to take a few minutes to kind of outline a strategy you can use when confronting a factoring problem. The first step should always be factor the greatest common factor from each term. We always want to look for that first. Then we want to consider the factors that contain more than one term. We're going to have binomial factors or trinomial factors for the most part. Is there a binomial factor that is the difference of squares? Well, if there is, we have a formula we can use to factor the difference of squares. Is there a binomial factor that is the difference of cubes? Well, we have a formula to factor the difference of cubes. Is there a binomial factor that's the sum of cubes? Well, if there is, we're going to pull out our formula for factoring the sum of cubes. Now let's think about what we do when we confront a trinomial factor. Well, we have formulas for perfect square trinomials. If we have a perfect square trinomial, it's either in the form a squared plus 2ab plus b squared, in which case we factor into a plus b quantity squared, or it's in the form a squared minus 2ab plus b squared, and that factors into a minus b quantity squared. So now if we have a trinomial factor that's not a perfect square trinomial, well, what do we do? Well, we can try factoring by grouping, or we could just try factoring by trial and error. Finally, if there's a polynomial factor with 4 terms, if we're lucky, it will factor by grouping. Otherwise, we will need more tricks than we're going to present to you in Math 65. Finally, when all is said and done, check the factorization by multiplying the factors. So here's our first example, 25x to the 4th minus 20x squared plus 4. When I look at those 3 terms, I notice that the 3 terms do not share any common factor other than 1. So now I've got to work to see what I have to do next. I've got a trinomial here. And one of the things I notice about my trinomial right off the bat is that the first term, 25x to the 4th, is a perfect square. Perhaps this is a perfect square trinomial. So what I'm looking at here is the possibility that a is 5x squared, because that squared is 25x to the 4th, and b is 2, because 2 squared is 4. So I'm thinking that this will factor into 5x squared minus 2 quantity squared. But I need to check that the coefficient on the x squared term is correct. Is that minus 2ab? So just checking, a squared minus 2 times a times b plus b squared. I want to confirm that the two sides of this equation are indeed equivalent. And 2 times 5 times 2 is 20, so everything works out. So this is going to factor into a minus b quantity squared. Now, just like in Steve's part of the lesson, I'm going to leave the checks for you. Here's another example. 8x to the 5th plus 27x squared. Do the terms have a greatest common factor? Well, they do. And that's a good thing, because that x to the 5th doesn't look like something I'm accustomed to working with in the problems that we've been doing. So both terms share a common factor of x squared. And I'm going to start by factoring that out. That leaves behind 8x cubed plus 27. Now when I consider the binomial factor, one of the things I notice is that is the sum of cubes. And we've just learned a formula for factoring the sum of cubes. What are the expressions that are being cubed? Well, we have 2x quantity cubed plus 3 cubed. So in our formula for the sum of cubes, a will be 2x and b will equal 3. So as I continue my factorization, I don't want to lose that factor of x squared that I factored out at the beginning. And what I leave behind is a plus b, so that's 2x plus 3 times a squared minus ab plus b squared. So a squared in this case is 4x squared minus a times b, that's 6x, plus b squared, which is plus 9. So do take a few minutes to check this factorization, because it's great practice multiplying polynomials. 25x to the 4th minus 4. This is the difference of squares. 4 and 25 don't have any common factors, but I do see the difference of squares. So 25x to the 4th minus 4. The perfect squares are 5x squared squared minus 2 squared, and this factors into the product of conjugates. 5x squared plus 2 times 5x squared minus 2. So in this example, I have a polynomial with 4 terms. First thing I want to check is that whether or not the 4 terms have some common factor. Well, they do, but in this case, the only common factor is 1. So with a 4-term polynomial expression, the only hope I have that I might be able to do some factorization is if I can factor this polynomial by grouping. So I'm going to give it a try. 12x cubed plus 16x squared minus 3x minus 4. When I look at the first 2 terms, they share a common factor of 4x squared. That leaves behind 3x plus 4. If I can factor this by grouping, I want a second term in this expression with a binomial factor of 3x plus 4. Can I get it? Well, I certainly can if I factor a -1 from the last 2 terms in my polynomial. Now I have a common binomial factor of 3x plus 4, leaving behind 4x squared minus 1. Well, now I have a binomial factor remaining. Can I factor that? Well, I can. That is the difference of squares. And it's the difference of squares where a is 2x and b is 1. So not forgetting that factor 3x plus 4, factoring 4x squared minus 1 into the product of conjugates, that's going to be 2x plus 1 times 2x minus 1. One last example. X squared minus 16x minus 64. Do these terms have a greatest common factor? Well, only common factor is 1, so I've got to try something else. This is really looking like a perfect square trinomial. So I'm going to factor this into x minus 8 quantity squared. But since you're about ready to take your test with Candace, I'm going to do a check. When I do a check, x minus 8 quantity squared, that's x minus 8 times x minus 8. When I multiply that out, I get x squared minus 16x like I want, but the product of the last terms is positive 64. So those two expressions are not equal. Well, can I factor x squared minus 16x minus 64? So is this trinomial factorable? It's not a perfect square trinomial. Well, we have a way to check. So what I want to do is I want to see, are there any integer factors of negative 64 that add to negative 16? Well, let's write down the factors of negative 64. In this case, I want them to add to a negative number. So the factor that's larger in magnitude needs to be negative. So I have negative 64 and 1, negative 32 and 2. 3 doesn't divide into 64 evenly. 4 does. Let's see. 5 does not. 6 does not. 7 does not. 8 does. But when I get here, I end up with 0 as my sum. And anything I choose after this, for example, if I choose negative 4 and 16, I'm going to end up with a positive sum, and I want a negative sum. So negative 64 plus 1, negative 32 plus 2, negative 16 plus 4, nothing works. Nothing adds to negative 16. So I've just done a very thorough check. I suspected that this trinomial was prime. Now I'm certain. Even when I'm taking the test, I don't want to assume that it is factorable. I did a check, and it is prime. So the trinomial x squared minus 16x minus 64 is prime. So with this, I'm going to turn it over to Candace, who's going to work through those examples that were on the factoring test. But you need to work them first. Those should be in your telecourse packet.
So in the last part of this lesson, I'm going to go through the factoring tests that you should have completed in your telecourse packet. If you're watching this on tape and you haven't done this factoring test yet, I suggest you stop the tape and go do the factoring test first. I'm going to go through these problems rather quickly, assuming that you've already done your factoring test. Let's start by factoring x squared minus 16. Well, it looks to me like I have a couple of perfect squares here, x squared and 16. And since I see subtraction, this looks like a difference of squares. So I think this x squared minus 16 factors as the quantity x plus 4 times the quantity x minus 4. Now, if you were actually taking a test, you would want to make sure that you check all of your work. So in this part of the lesson, I'm going to check every factorization that I do, and I'm going to write the checks out. So let's check this. What do I get when I multiply the quantity x plus 4 by the quantity x minus 4? Well, foiling this out, I have x squared minus 4x plus 4x minus 16. Minus 4x plus 4x is 0, so I have x squared minus 16. That's the polynomial I started with, so my factorization is correct. Now let's factor 5x squared minus 125. Anytime that we're factoring, the first thing that you want to look for is a greatest common factor of all the terms. In these two terms, I see a greatest common factor of 5. So I'm going to start by factoring out 5 from these two terms. When I factor out of 5, I leave behind x squared minus 25. Now I need to look at the binomial x squared minus 25 and decide whether I can factor this any further. X squared minus 25 looks like another difference of squares. So I think this factors as x plus 5 times the quantity x minus 5. And notice that I didn't forget that first factor of 5, the greatest common factor I factored out as my first step. I want to make sure that I have the correct factorization, so I'm going to check this. I'm going to check this in a little bit different order, just so that I try not to make the same mistake I might have made when I was doing the initial factorization. So I have 5 times the quantity x plus 5 times the quantity x minus 5. Now instead of multiplying what I think was a difference of squares first, I'm going to distribute the 5 through the x plus 5. That gives me 5x plus 25. And I still need to multiply that by the quantity x minus 5. So foiling this out, I have 5x squared minus 25x plus 25x minus 125. Minus 25x plus 25x is 0, so this simplifies to 5x squared minus 125. That's the polynomial I started with, so my factorization checks. Now let's factor 5x squared plus 125. Well, right away I notice I can factor out a greatest common factor of 5, just like in the last problem. When I do that, I leave behind x squared plus 25. Looks like I have a couple of perfect squares again, x squared and 25. Can I factor the binomial x squared plus 25? Well, this time it's not a difference of squares because I'm adding. What I could think about is a middle term of 0x. Do I have two integers that multiply to 25 and add to 0 to give me that coefficient of the middle term? Well, two integers that multiply to 25 are never going to add to 0. So this polynomial looks like it's completely factored. I think the check is easy enough that I'll just check this in my head, because all I have to do is distribute the 5 through the parentheses. 5 times x squared is 5x squared. That checks. 5 times 25 is 125, so the second term checks as well. Now let's factor x squared plus 5x plus 6. I don't see any greatest common factor to all three terms other than 1. So I just want to think about how I can factor this trinomial. Well, I think that I can probably do this one by guessing and checking. I'm looking for two integers that multiply to give me 6 and add to give me 5. 2 and 3 do the trick. So I think this factors as x plus 2 times the quantity x plus 3. But of course I want to check this. So what happens when I multiply x plus 2 by x plus 3? Well, foiling this out, I get x squared plus 3x plus 2x plus 6. Combining my like terms, I have x squared plus 5x plus 6. That's the polynomial I started with, so this checks. Now, when you did your factoring test, you factored this problem by grouping and came up with the right answer. That's great. Remember, we have different strategies for factoring. Guess and check was one of them. Factoring by grouping is another strategy. Now let's factor x squared minus 7x plus 12. Again, I don't see a greatest common factor to all three terms other than 1. So I want to think about, how do I want to factor this trinomial? Do I want to guess and check? Do I want to factor by grouping? I think I'm going to try guessing and checking. I want two integers that multiply to give me 12 and add to give me negative 7. Well, negative 3 and negative 4 multiply to 12 and add to negative 7. So I think that x squared minus 7x plus 12 factors to x minus 3 times the quantity x minus 4. Let's check that. What do I get when I multiply x minus 3 by the quantity x minus 4? Foiling this out, I have x squared minus 4x minus 3x plus 12. Combining the like terms, negative 4x and negative 3x add to negative 7x. So I have x squared minus 7x plus 12. That's the polynomial we started with, so this checks. Again, if you did this by factoring by grouping, that's fine. Let's factor x squared minus 6x minus 15. This time I'm looking for two integers that multiply to give me negative 15 and add to give me negative 6. I'm not thinking of anything right away, so I think I'm going to make an organized list. So again, I want two integers that multiply to give me negative 15 and add to give me negative 6. Well, let's see. 1 times negative 15 is indeed negative 15, but that adds to negative 14. 2 doesn't go into 15. 3 times negative 5 is negative 15. That adds to negative 2. 5 times negative 3, that multiplies to negative 15, but that adds to positive 2. My only other choice would be 15 times negative 1, and again, that's going to give me a positive sum. So I've looked at all of the possibilities of integer factors of negative 15, and none of those add to negative 6. So that tells me the trinomial x squared minus 6x minus 15 is prime. And since I don't have a factorization to check, the only thing I can do is look through my organized list and make sure that I really did get all of the factors of negative 15. And it looks like I did. Let's factor 2x squared plus 6x minus 20. Well, right away I notice that all of those coefficients and the constant at the end are even. So I'm going to start by factoring out 2. That leaves behind x squared plus 3x minus 10. Now I want to think about factoring the trinomial in parentheses. Can I factor x squared plus 3x minus 10? Well, are there two integers that multiply to give me negative 10 and add to give me positive 3? How about 5 and negative 2? So I think this factors to 2 times the quantity x plus 5 times the quantity x minus 2. But I want to check. So I'm going to distribute the 2 through to the binomial x plus 5 as my first step in my check. That gives me 2x plus 10, which I still need to multiply by x minus 2. Foiling this out, I have 2x squared minus 4x plus 10x minus 20. Combining my like terms, I have 2x squared plus 6x minus 20. That's the polynomial I started with, so this checks. Let's factor 2x squared plus 3x plus 1. I don't see any common factor to all three terms other than 1. Since my coefficient on x squared is something other than 1, factoring by grouping might be a good idea here. But if I look a little bit closer, 2 is prime, and that constant 1 at the end only has factors of 1 and 1. I think there's only one possibility here. 2x and x for my first terms of my binomials to give me the 2x squared, and plus 1 and plus 1 for my last terms of my binomials to give me that constant of 1 at the end. I said this was the only possibility, but that doesn't mean that it works. So let's go ahead and check. When I multiply 2x plus 1 by x plus 1, I get 2x squared plus 2x plus x plus 1. Combining like terms, I have 2x squared plus 3x plus 1. That's the polynomial I started with, so this checks. Now let's factor 2x squared plus 3x. The first step in any factoring problem is to look for a greatest common factor. 2 and 3 don't have anything in common, but both terms do have a factor of x. So if I pull out that greatest common factor of x, I leave behind 2x plus 3. 2x and 3 don't have anything in common, and 2x plus 3 is a linear factor, so I can't factor this any further. I can do a quick check in my head because all I have to do is distribute the x through to the 2x and the 3. X times 2x is 2x squared, x times 3 is 3x, so this checks. Now let's factor 3x squared plus 5x minus 2. This one I might be able to guess and check. I think I want to do factoring by grouping. So that coefficient of x squared is a 3. I've got that minus 2 at the end. I'm looking for a product of 3 times negative 2, which is negative 6, and a sum of 5, which is the coefficient of the middle term. So are there two integers that multiply to give me negative 6 and add to give me positive 5? Well, how about 6 and negative 1? That sum is definitely 5. So I'm doing factoring by grouping here. What I want to do is rewrite 5x as 6x minus 1x. So 3x squared plus 5x minus 2 can be rewritten as 3x squared plus 6x minus x, 6x minus x is 5x, minus 2. Now I want to group the first two terms together and the last two terms together. The first two terms have 3x in common. If I factor out 3x, that leaves behind x plus 2. The last two terms, well, the only thing that I can see in common is a negative 1. And I do want to pull that out because I want a factor of positive x plus 2. So if I factor out a negative 1, I leave behind positive x plus 2. Now I have a common binomial factor of x plus 2. If I pull out that factor, I leave behind 3x minus 1. But I want to check this to make sure that this factorization really does work. So here I want to multiply x plus 2 by 3x minus 1. Foiling this out, I have 3x squared minus x plus 6x minus 2. Combining like terms, I have 3x squared plus 5x minus 2. Endless checks. So now let's factor 4x squared plus 8x minus 16. Well, it looks like I have a bunch of multiples of 4 here. Is there anything other than 4 that I can pull out as a greatest common factor? It doesn't look like it. So I'm going to start by factoring out a 4. When I do that, I leave behind x squared plus 2x minus 4. Can I factor this trinomial, x squared plus 2x minus 4? Well, let's see. Are there two integers that multiply to give me negative 4 and add to give me 2? I'm not thinking of any, but let's go ahead and make a list and make sure. So we're looking for a product of negative 4 and a sum of positive 2. There aren't too many factors of negative 4. Negative 4 and positive 1 would give me a sum of negative 3. That doesn't work. Negative 2 and positive 2 would give me a sum of 0. That's not what I want. Negative 1 and positive 4 is my only other choice. That gives me a sum of positive 3. So x squared plus 2x minus 4 is prime, which means this polynomial is already completely factored. I can do a quick check in my head by distributing the 4 back through the parentheses. 4 times x squared is 4x squared. 4 times 2x is 8x. 4 times negative 4 is negative 16. So my factorization appears to be correct. Now let's factor 4x squared minus x minus 3. I don't see any common factors to these three terms other than 1. So I just want to think about, how do I factor this trinomial? Well, I'm looking for integer factors of 4 times negative 3. That's negative 12. And I want a sum of negative 1. Are there two numbers that I can multiply together to give me negative 12 and add together to give me negative 1? Well, sure. Negative 4 and positive 3. That gives me a product of negative 12 and a sum of negative 1. So I want to rewrite that middle term opposite x as negative 4x plus 3x. So 4x squared minus x minus 3 is 4x squared plus 3x minus 4x. 3x minus 4x is minus 1x. There's my middle term. And I have a minus 3 at the end. The first two terms have an x in common. When I factor out x, I leave behind 4x plus 3. The last two terms, well, it doesn't look like those have anything in common other than negative 1. If I pull out negative 1, I leave behind 4x plus 3. That's good. Now I have the same binomial factor in both terms. If I factor out 4x plus 3, My other factor is x minus 1. Let's go ahead and check this. So what do I get when I multiply 4x plus 3 by x minus 1? Well, I get 4x squared minus 4x plus 3x minus 3. Combining like terms, that's 4x squared minus x minus 3, which is the polynomial I started with, so this checks. Now let's factor 4a squared minus 49b squared. I don't see any common factor to both terms other than 1. However, I am observing that 4a squared is a perfect square, and 49b squared is a perfect square, so it looks like I have a difference of squares. So 4a squared minus 49b squared, I think will factor as 2a plus 7b times the quantity 2a minus 7b. But of course I want to check to make sure that this factorization really works. So what do I get when I multiply 2a plus 7b times 2a minus 7b? Well, I get 4a squared minus 14ab plus 14ab minus 49b squared. Negative 14ab and positive 14ab add to 0, so I'm left with 4a squared minus 49b squared, which is the polynomial we started with. So this factorization checks. Now let's factor 3n cubed minus 2n squared plus 12n minus 8. I'm not seeing any factors common to all four terms other than 1. Since I have four terms, the only factoring option I really have open to me right now is factoring by grouping. So let's see if this polynomial can be factored by grouping. The first two terms have n squared in common. If I factor n squared out of the first two terms, I leave behind 3n minus 2. The last two terms have 4 in common. If I factor 4 out of the last two terms, I leave behind 3n minus 2. So I do have a common binomial factor, 3n minus 2. If I factor that out, I leave behind n squared plus 4. N squared plus 4 is a sum of squares which cannot be factored, so I can't factor this any further. I do want to check my factorization though. What do I get when I multiply 3n minus 2 by n squared plus 4? Well, I get 3n cubed plus 12n minus 2n squared minus 8. And other than those second and third terms being in a different order, I do indeed have the same polynomial that I started with, so this factorization checks. Now let's factor m squared minus 12m plus 36. I don't see any greatest common factor to all three terms other than 1. I am noticing that m squared is a perfect square, and that last term, 36, is a perfect square. So perhaps this is a perfect square trinomial. Well, let's think about it. If this factored as a perfect square trinomial, we'd get the binomial m minus, because of that minus 12m, 36 is 6 squared, so m minus 6 quantity squared. Let's check to see if this works. M minus 6 quantity squared means m minus 6 times m minus 6. And if I FOIL that out, that's m squared minus 6m plus 36. Combining like terms, that's m squared minus 12m plus 36. And that checks. If when you were doing the factoring test you didn't recognize this as a perfect square binomial, but you were still able to factor it, that's great. In a testing situation, that might not be the first thing that occurs to you. But if you think about integer factors of 36 that add to negative 12, negative 6 and negative 6 do the trick. Now let's factor m squared minus 25m plus 25. This looks a lot like the last problem. M squared is a perfect square. 25 is a perfect square. So let's see if this is a perfect square trinomial. If that's the case, this should factor as m minus 5 quantity squared. Well, let's check. What do I get when I square m minus 5? Well, this means 2 factors of m minus 5. Foiling this out, I have m squared minus 5m plus 25. When I combine like terms, I have m squared minus 10m plus 25. I didn't want minus 10m for my middle term. I wanted minus 25m. So this doesn't work. Well, is there any other way that we can factor m squared minus 25m plus 25? Let's try. Let's see, we're looking for two integers that multiply to give us 25 and add to give us negative 25. Nothing's coming to me right away, so let's look at an organized list of the integer factors of 25. I know they both need to be negative since I want the product to be positive 25, and I want a sum of negative 25. Well, let's see. Negative 1 and negative 25. That adds to negative 26. Negative 5 and negative 5. That's what we tried for our perfect square trinomial technique. That gave us minus 10m as our middle term. And that's all of our choices. 25 doesn't have too many factors. So it looks like the trinomial m squared minus 25m plus 25 is prime. Now let's factor k cubed plus 8. Definitely no common factors to these two terms other than 1. It looks like I have a sum of cubes. K cubed is a perfect cube. 8 is 2 cubed. So if we remember our formula for factoring a sum of cubes, we need a plus b. In this case, that would be k plus 2. And we multiply that by a squared minus ab. Remember, we changed the sign on the ab, plus b squared. So a squared would be k squared, minus ab would be minus 2k, plus b squared would be plus 2 squared, which is plus 4. Remember, anytime we factor a sum of cubes, that trinomial factor doesn't factor any further. So let's check our work. What do we get when we multiply k plus 2 by k squared minus 2k plus 4? Distributing the k through the trinomial gives us k cubed minus 2k squared plus 4k. Distributing the 2 through the trinomial gives us plus 2k squared minus 4k plus 8. Combining like terms, well, negative 2k squared plus 2k squared adds to 0. 4k minus 4k also adds to 0. So all that we're left with is k cubed plus 8. That's the binomial we started with, so the factorization checks. Now let's factor 3a squared plus 15ab plus 18b squared. 3, 15, and 18 are all divisible by 3. Is there anything else in common to all three of these factors? It doesn't look like it, so I'm going to start by pulling out the greatest common factor of 3. If I factor out a 3, that leaves behind a squared plus 5ab plus 6b squared. Can I factor the trinomial in parentheses? Well, can I find two integers that multiply to give me 6 and add to give me 5? Sure, 3 and 2. So keeping that original greatest common factor of 3 as my first factor, a times a will give me a squared, and I know 2 times 3, both positive, multiply to 6 and add to 5. but I need that b squared at the end there. So if I add 2b and add 3b, this should work. Let's check to make sure though. So what do I get when I multiply 3 by the quantity a plus 2b by the quantity a plus 3b? Distributing the 3 through to the a plus 2b gives me 3a plus 6b. And I still need to multiply this by a plus 3b. Foiling this out, I have 3a squared plus 9ab plus 6ab plus 18b squared. Combining like terms, I have 3a squared plus 15ab plus 18b squared. Looking back to my original trinomial, this appears to be correct, so our factorization checks. This is the end of our factoring test. If you are actually taking a factoring test in class and you had some extra time, it would be a good idea to go back and check all of your work again.